Thank you. So thank you for joining today's session. My name is Karim Maslout. I am the Manager of International Projects at Premier Corex. Thank you very much for joining us. If you are have joined us before, welcome back. If this is your first session, thank you for being here. We hope that you find this session informative and gain some valuable technical insights. Today's topic is core analysis as an aid to understanding reservoir water saturation distribution. Okay, and hopefully you'll find that interesting. Next slide, Greg, please.
Hey.
Yeah, next one.
All right.
Okay, so quick housekeeping rules. Please use the Q&A panel to submit your questions at any time. We will answer all questions at the end of the session. The session is being recorded. The time is about 45 minutes with about 15 minutes at the end for the Q&A part. All attendees are muted during this webinar. Audio is not enabled. At the end of the webinar, you will receive a link to the recording. You will also find the recording on our YouTube channel later on. Okay. Next slide, please. So introducing our guest speaker for today is Craig Lindsay from Core Specialist Services. He is the founder of Core Specialist Services since 2010, and he specializes in all aspects of coding and core analysis. He has over 44 years of experience across well site operation laboratory and consultancy. He is the former president of the Society of Core Analysts between 2012 to 2013, and current industrial relation liaison. Current president of the Aberdeen Information Evaluation Society and active contributor to the Society of Petroleum Engineers, Society of Petrophysicists and Well Log Analysts, and Rock Imaging Special Interests Group. Quite a CV, Craig. Thank you very much, and it's a pleasure to have you. So over to you to start your webinar.
Yeah, thanks very much for the introduction and for inviting me to present today. It's a great honor. So it's quite a big subject, this, but it's one I've been very interested in for a long time. I think what my experience is, people can make it very complicated, but my view is actually you don't need to make it complicated to understand what's going on. And I hope that some of the material I show today will make that case for it being relatively simple to grasp the concepts. So during today, we're going to look at some of the things that control the distribution of water saturation in a porous media in a reservoir, and then some of the terms that go with that. And then we're going to look at the core aspects of that, how we can understand water saturation in a reservoir from core analysis, and we'll look at some applications and illustrations. And I should note there that obviously things I had to make things quite simple to make them explainable to everyone, and that is the case. So it's just for brevity. Things are in reality can be more complex, but for our purposes today, they should be fit for purpose. So we want to understand how hydrocarbons and other fluids are able to be accumulate in a reservoir, and basically that down to the density difference or the buoyancy effect, which is a primary control on the fluid distribution. Hydrocarbons, but also hydrogen and carbon dioxide are in the gas phase, and liquid oil are less dense than water. And they're also immiscible with water. Both of those things are very important. So you can see there I've got a measuring cylinder with oil and water in, and we all know it, that oil floats on water. And so that separation is driven by gravity, and the greater the density difference between the phases, the stronger the buoyancy force is. And in the diagram here, I'm showing what you would see would be a water pressure gradient, followed by an oil pressure gradient, followed by a gas pressure gradient in the subsurface. So the gas is less dense than the oil, which is less dense than the water. And pressure at any point, a fluid column increases with depth. If you want to know more about what these effects look like in zero gravity, check out the links I put in below. Real interesting stuff, experiments on the International Space Station. So I've put together some illustrations of fluid density units and typical buoyancy gradients, and there's different ways of looking at. We usually look at fluid density in grams per cc, but other places use other units. My comfort zone or default is pressure gradients in psi per foot. And so that's what I've shown, and you calculate that using the small formula I've shown. And most fluids in the reservoir have a range of composition, which gives them a range of density. And I've shown some there for obviously dry gas being the least dense. That table is obviously in order of density from least dense at the top, dry gas to the brine most dense at the bottom. And then I've shown some densities for CO2, which is obviously quite relevant to a lot of things we're doing nowadays, looking at carbon capture and storage and so on. But one thing to note is actually in its densest phase, liquid CO2 is denser than water. So at some point it can start to go underneath the water, and that's important. In the reservoir, well logging tools measure pore pressure. And from, if we go back to the previous slide, it kind of, if we think of a pore pressure gradient, you can measure multiple points on a pressure gradient, and you can build that into, from those pressure measurements, you can calculate the density gradient. So I'm referring to this constantly as buoyancy rather than pressure, because I think if you think of buoyancy, it always a lot of people talk about capillary pressure and pressure gradients, but it's all about buoyancy. So I think that's a good way to think about it. And so when you have an accumulation of, let's call it oil and water, where the pressure gradients intersect, that is what we call the free water level. And beyond that point, you can project the water pressure gradient, and you can project the hydrocarbon pressure gradient. Again, I've shown some pressure points here, but the intersection is where we have the free water level. Now, at that intersection, you have zero, effectively, buoyancy pressure. There's no buoyancy pressure, but as you increase in height above that free water level, the buoyancy pressure increases, and it's a function of the difference in density between those two fluid phases. So if we look at the example here where we have a typical oil density 0.3 psi per foot and a water density 0.45 psi per foot, with a 100-foot column, you would have a 15 psi buoyancy pressure at the top of that 100-foot column, 0 at the bottom, 15 at the top, and obviously incremental between those limits. So that fluid property, the density difference is a very primary control on water saturation distribution. Now, another very primary control is the pore throat size, because what we have to do when this buoyancy force has to exceed what's called the pore entry pressure of the pore network. And so the larger the pores, the lower the pore entry pressure, and the smaller the pores, obviously vice versa. So if we're looking at a sort of cartoon of a pore network, you can see large pores with water in them, and then some smaller pores. So this equation here, the Young-Laplace equation, shows us how a pore throat size controls this pore entry pressure, the PCE. The other factors which control that are fluid properties, fluid and rock properties, which is the interfacial tension. That's a fluid system property. That's the between the oil and the hydrocarbon, or sorry, the hydrocarbon and water. And then the contact angle is a property between the rock and fluid. However, really, the dominant factor here, I'll show that later, is the pore throat radius. And obviously that tends to have a strong link to rock quality, large pore throats, good rock quality, and vice versa. And this pore throat entry pressure, it defines the next thing we're interested in, the hydrocarbon water contact. Now, this is an image which I've came across a long time ago, and it's really, I could talk about this one all day. In fact, this single slide really sort of captures all the things we're sort of interested in to do with hydrocarbon accumulation. It was created by someone back, Mike Roberts, back in the 1970s. Can't find any of a trace of him. That's all he did, or that's all he's left in the sort of to be found. But it's a fantastic legacy as far as I'm concerned. So it shows a figure of these hydrocarbons trying to force their way out of the large pores into the small pores, and they're having to use a lot of force, but they can't get in there because they haven't exceeded the pore entry pressure. So it shows that these large pores have already filled with hydrocarbon, and then there's a transition into smaller pore throats, and the oil is trying to enter those smaller pore throats. So it's the pore throat size is a primary control on hydrocarbon invasion. And the other thing to note is that pore throat size can vary, well, in a real reservoir will vary vertically and laterally. So water saturation will change not just vertically, but laterally due to rock quality changes. So the impact here of rock quality and hydrocarbon water contacts, we talked about the free water level. Now, the free water level should be a planar surface because it's that place where the pressure gradients intersect, and the pressure difference, the buoyancy difference is zero. Should be a flat surface. It isn't always, but let's call it a flat surface. But because the pore entry pressure varies with rock quality and porosity and permeability, that means that the minimum level at which hydrocarbon can enter the pore system will vary across the reservoir. According to the fluid types, whether it's gas or water, and according to the rock quality itself, which controls these buoyancy forces. So you can see in the diagram at the bottom here, we have some, schematic layers. A real reservoir wouldn't look much like that, but it illustrates that where the rock quality is good, the pore entry pressure is low, and so we get the oil water contact or hydrocarbon water contact close to the free water level. And then we have other layers where the rock quality is less good, and finally you have a layer where the rock quality is poorer, and so you can have a free water level sort of oil water contact which is tens or even hundreds of feet above the actual free water level. And of course the key thing to remember is ultimately the top of the hydrocarbon column we have a seal. And that seal, the entry pressure of that seal must be greater than the buoyancy pressure of that hydrocarbon column. Otherwise, it can't hold the hydrocarbon. And we can see that a good seal may have an entry pressure of thousands of psi even, or it may have no pores at all. We looked recently at some halite, which is a partial barrier, one of the seals in the southern North Sea for carbon capture and storage complex projects, and actually it's got no pores at all. So it's impossible for fluid to enter it by capillary forces. You could have enough mechanical forces perhaps, but not by capillary forces. So it's an excellent seal, and that is a necessary component of all reservoirs, including carbon capture and storage projects. Now, we go back in time, a long time, to 1899, where there's a book put together about soil properties. And at that time, this gentleman, Mr. Ford, he created some columns of sand and different types of soil, which were about 12 feet, about 3 or 4 meters high. As you can see, there was 4 columns here. And what he did, he filled them with these soils and then filled them with water, effectively sealed them so there was no evaporation, but allowed the water to drain out of them, and monitored them for about 2 years before he dismantled them and took samples to measure the water content by weight. And then what the data that's in the book isn't shown as charts, but I created charts. And what we see is that effectively we have the heights up here, 8 feet of the column. We have the water saturation along the bottom. And what we see is that there's a pressure gradient or buoyancy gradient, if you like, of about 5 psi between that top and the bottom. And this is exactly the same. This thing happens in soils. Obviously we have evaporation in a real world, but actually it's the same controls on water saturation in soils. And in fact, the porous plate, which is one of the instruments we use, was developed for soil science. But anyway, what we see is that if we call the bottom here the free water level, we have pretty high water saturation at the bottom, and then different soils behave in different ways as we go up the column until we reach quite a low saturation at the top. Now, this is exactly what we see in reservoirs, and so this early work was then used by people and looked at, and from early days in the oil industry, when we started to have well logs available and so on, people saw similar profiles and they needed to explain what was going on. And they saw these patterns emerge, that there was a zone near the base, perhaps of the free water level, where there was completely saturated, and then we had a zone where the water saturation could change quite rapidly, and then we had a zone where the water saturation was not changing so much, had gone to a low level. And I think at that time, these terms, a transition zone and what we call irreducible layer, or they call it a pendular zone, were originated. These terms originated them and used to this day, but they can be quite confusing. So a transition zone is, well, it's something where the water saturation is changing with height above the free water level. But it can be hard to define what changing actually means. What does it mean? I mean, we look at two different examples here. I'll show a few charts. In each case, it assumes these curves, if you like, assume that the rock quality is uniform for that 100 feet of column. It wouldn't be in reality, but it's just to illustrate. So we have the curve on the left here, and we can say, well, water saturation is changing rapidly, and then it sort of slows down. Is that a transition zone? And then we look at the example on the right, and it's the saturation is changing much more slowly, and it's still changing at the top of that 100 feet column. Is that a transition zone? Well, maybe, but it's a bit of a confusing term. All we can say is that the water saturation is changing, and mainly other factors control what people call a transition zone, and I've got a slide on that later. But it's always rock quality drives that in a given fluid system. And then we've got this other term, the irreducible water saturation, or we could say a water saturation no longer decreases. Now, again, looking at those two same curves, you could say, well, where on that curve does the water saturation stop decreasing? And you can say, well, actually, it's still decreasing at the top. And it is. And in fact, there's no such thing as irreducible water. It's highly improbable or even impossible. I said in very rare cases where you have a very narrow porphyroid size. So it's a concept. It's again controlled by the buoyancy gradient, the fluids in the system, and rock quality. You know, how extensive this section is where water saturation is changing slowly. But in fact, water saturation would generally continue to decrease. But what we can say is, for practical purposes, probably above a certain point, water becomes effectively immobile, and we can call that non-mobile, but I would not call it irreducible. So I've got some examples here of the things I've been talking about, how those affect in a set of these same set of curves. So I've told you that in the subsurface, the buoyancy, the drainage, it's a drainage process, and it's driven by buoyancy, which is gravity driven. So it's quite similar to what happens in soils on the land surface, but with obviously pressure gradients much higher. So and it's a function of the fluid type, with the gas or oil can enter pores or not, and the density difference and the pore throat radius. So we've got here the first image, and in each case we've got water saturation along the bottom, and we've got the buoyancy pressure or the height above free water level on the vertical axis here. And so these curves illustrate the same fluid system on this first image on the left, same fluid system, but different rock qualities. So the left-hand curve is a high rock quality, say 500 millidarcies, 25% porosity. The blue curve is say 100 millidarcies, 15% porosity. And so because of that, the pore throat sizes will be different, and that affects how much fluid that can enter those pores as a function of height above free water level, less in the case of the lower quality rock. Now, moving over to the center image, all I've done here is change the buoyancy gradient. So the rock quality of those that goes into calculate those two curves is exactly the same. However, I've changed the buoyancy gradient, and I think the red one is a gas type buoyancy gradient, and the blue one is more an oil type gradient. So you can see that the curves are shifted because we've changed the fluid type. And then we've gone over to the right hand image, and I've changed the interfacial tension and contact angle. That wouldn't normally change on its own, but for the sake of a demonstration, I've just left it as that. So you can see that definitely affects things, but not so much. So the primary controls of the pore throat radius, the rock quality, and the fluid properties. And this is just another, I think this comes from Schlumberger somewhere, that it's an illustration of these concepts with a free water level. You've got a resistivity curve, you've got a fluid saturation curve, and you've got an entry pressure before a hydrocarbon really gets into a pore system. You've got the free water level, oil water contact, you've got the two gradients, oil and so water and hydrocarbon, with some pressure points which are used to create that intercept. So now we come on to the bit of our core analysis. Now I've got four or five points here, and to be honest with you could talk all day about all of them, but we've got only a half hour, so I'll do what I can in that time. So we can measure core water saturation on core that's come in from a well. We can conduct experiments that mimic buoyancy effects, these buoyancy effects, and induce drainage of water from a core. And we can define a pore entry pressure and pore throat radius versus buoyancy pressure from core analysis. And we can account, of course, we need to and have to account for the differences in conditions between lab and reservoir before we can apply these data in the subsurface. And then we can go on to model these data to calculate water saturation distribution in the subsurface. So a lot of things we can do in core analysis, very, very important. So you've probably all come across Dean Stark, which is a way to measure water saturation on fresh state cores. And those fresh state cores will contain a number of different fluids, including formation water, hydrocarbon, drilling fluid filtrate, and so on. And we have to remember when we conduct these tests that there are things that happen to the core as it's brought to the surface. Pressure can change and fluid saturation can change. I'll come on to that in the next stage. The Dean Stark consists of the distillation process, where we distill the water out of the core and collect it, and we adjust the volumes to take account of the actual brine in the reservoir, because we collect distilled water in the lab, and then we measure a pore volume on the core sample and use that to calculate a fraction of that pore volume, which is the water saturation, and we apply corrections for salinity and formation volume factor and also overburden. It's a low-cost method. In my view, it's perhaps the single most useful low-cost method that we have in core analysis. It's fantastic. And the sequence of tests, sequence of apparatus, there's quite a few steps to it. I'm not going to go through them all, but the point is that there's a number of stages of drying and extraction and solvent, weighing, collecting things, measuring things. Each of these steps have to be carefully conducted and done without error in order to make sure that the data at the end of the test is correct. Of course, that's standard practice for the labs, but it's just overseen sometimes from the outside that actually it's quite a complex procedure. However, it certainly is one of the best procedures I'm aware of. Again, this is a summary. I'm not really going to go through all the points one by one, but it's talking about the different factors that can affect what we see in a water saturation from a Dean Stark. And there are some factors which can mean that the water, because as I said, when we get a core in the lab, things will have changed in it. We hope it hasn't changed too much, but things will have changed. And some processes can operate to reduce the water saturation that we see in the lab compared to what it is in the reservoir. And some processes can operate to increase the water saturation. We hope that those processes are minimized, and if we are aware of the factors that can impact or cause these changes, then we can hope to have a best possible water saturation represented the reservoir, but it will never be exactly the same. So we call it an as received water saturation, or that's what I call it. And as I've got here, some of the factors that can reduce the water saturation, we can have some kind of flushing with drilling mud filtrate if the core water is mobile, some flushing. We can have gas expansion as the core's brought to the surface. We can have incorrect handling of the cores and so on, and problems with the lab if the tests are not conducted properly. We hope we don't have any of those, and I'm sure at Corex they follow every step to make sure this doesn't happen. And other things were less common, but things like if the water has been exposed, the core's been exposed to water, say at a well site or something like that, will increase the water saturation. However, in our best case scenario, where we have something like an oil-based drilling fluid, we're coring from that mobile water zone in the hydrocarbon column. We can aspire to have a Dean Stark data from a fresh state core as the benchmark. If we have water-based drilling fluid, we can still take measures. We can things usually like tracer compounds, which can be analyzed for, which can help to correct the water saturation we observe. So we can back calculate what the actual reservoir saturation should be. So here's some examples, some old examples that I have here. The one on the left-hand side was actually an EOR project, and took some core. However, because the water in the reservoir was mixed salinity, the log-based water saturation was quite suspect. So it was very important to be able to quantify the water saturation by Dean Stark. So what you see there is a pretty good match between the log and the Dean Stark. We would actually say in this case that actually though the Dean Stark is the benchmark. It's the ground truth, whereas the logs were more uncertain because of these mixed salinity affecting the resistivity calculation. And then on the left-hand example, it's pretty good. We see the core probably down to the certainly down to the contact, which is just near the bottom here, and we have the log-based water saturation, which is looking pretty good, and then we have the Dean Stark dotted along the saturation curve from the log. I think it was quite a dense fluid, so a low buoyancy gradient. So there's quite a slow change in water saturation. So we've looked at the measurement of fresh state water saturation in cores to understand that in the reservoir. And now we look briefly at what we can do in the lab to what we call simulate these drainage process. So we forcibly displace water from a rock using a fluid, usually a lab oil or gas. We can also use mercury using the high pressure mercury injection. Obviously, we don't have mercury in the reservoir, but mercury is useful because, I'll come on to that, has advantages in speed and other things. The buoyancy or drainage pressure is increased in steps. So all the three of these methods have the same principle, that we are simulating the drainage process, and pressure is increasing a series of steps to define the rate of change, or fit a curve to the change of saturation with buoyancy pressure. In the case of mercury, we subtract the mercury saturation from 1, and that gives us the equivalent water saturation. And we define a curve, and I'll show how that works. It's often called a drainage capillary pressure curve, but again, I think the capillary pressure can be a misleading term, but and generally the industry uses that term, and that's what you're most familiar with. And the shape of these drainage process curves is again controlled by the rock quality and the fluid properties. And we're able to then apply factors to correct the curves that we measure in the lab to reservoir conditions. I mentioned it's a stepwise process. On the left-hand illustration, you've got low pressure, medium pressure, and high pressure, and you see a series of steps going upwards until you get to what we call might be the final step, and that final pressure step might be picked based on what we think it might be in a reservoir. There's no point in going to a buoyancy pressure that we never see in our particular reservoir, or in some cases it's just picked it's often picked using mercury injection data to define where saturation is probably not going to change much more. So we see a real example here of a centrifuge, and we can see that sorry, I should have mentioned the previous slide. I didn't really mention it's a high-speed centrifuge, a porous plate, and a high-pressure mercury injection. So this is a centrifuge example where the speed of the centrifuge is stepping up over a series of steps. And each time it steps up, you can see that the water saturation, or produced water here, the blue curve, is stepping up, takes some time to stabilize. And when it's deemed by the lab to be stabilized, then we can move up to the next pressure, and the same thing, and so on and so on. So we get a series of pressure steps and a series of steps with water production, water drainage, which is used to define these curves. Now, I've produced some quite detailed schematics here, and they are very schematic, and I unapologetically have to admit that I used AI to help produce these images. I've checked them fairly carefully. They don't really sort of replicate typical equipment that you would see in a lab, but they do quite nicely capture some of the key elements and the principles which are involved. So when we have a core sample in a centrifuge, it starts saturated water. We have a reservoir of the draining fluid, the displacing fluid, which is oil or gas in the inner part of the centrifuge, and we have a capturing container in the outer part where the produced water is captured. And we increase those speed. We start to rotate the centrifuge, and we increase through a number of pressure steps. And at each stage, we record the water produced until we have that full set of data. The rotational speed of the centrifuge can be converted mathematically into a pressure, buoyancy pressure, capillary pressure. The downside of the centrifuge, the mathematics is quite complex. You really need quite a uniform sample. You have radial effects. There's quite a few things which can complicate the analysis of data. It's reasonably rapid, but as I say, challenging maths. porous plate. Now this is a method where, again, we have a draining fluid, and this time the pressure to the system is supplied by a gas, or usually a gas, could be a gas cap, could be a pump even, but we go through a series of pressure steps. This time we have a porous membrane at the bottom of the core, which is, and the core is maybe held in a core holder, and that membrane only allows brine to drain, but not the displacing fluid. So we go through a series of pressure slips and collect the water. We build up that, again, a series of pressure steps and production to build up this drainage curve. The system properties here, obviously it can be quite similar to a reservoir, because you've got the water, the brine. You can even use a crude oil, but you've got an oil, a gas, or a brine, and so that's reasonably equivalent to a reservoir. It's slow. It can be very slow. It can take at least 3 or 4 months. Can take 6 months. Can take a year. So, but it's a good benchmark for capillary pressure and these curves and so on. And then we've got that high pressure mercury injection, and often that's used. The industry standard system is called a microhemorrhagic system. You may have seen one if you've been around any core analysis lab. And again, the principle is exactly the same. We use the pump is used to push mercury through there is no fluid in the system. It's evacuated. It's a vacuum. And it's very difficult to push mercury into a porous media, because it's got a very high contact angle and interfacial tension sum. So we have to use high pressure. It covers a very wide range of pressure, from maybe 1 psi up to 60,000 psi, but the principle is exactly the same. We go through these pressure steps and we build up these curves. It's at least like a reservoir, but it's rapid, and it's a great source of data, and it's the only method to characterize pore throat size distribution. And this is just an example of what the pore throat size distribution might look like of a good quality sandstone. And each of the dots is a pressure step. So what you can see here is we've got very many pressure steps, and you can actually say that each pressure step we are picking up entry pressure of smaller and smaller pores. And so the mercury injection is able to produce a very detailed view of the core of the rate of change of saturation with pressure increase, and we call that the pore throat size distribution. And also we display the same information on the right hand side, where we see it's converted to a fluid system with oil, and the height above free water level we see a fairly slow, well, it's actually a fairly rapid decline actually, because it's only 10 feet above high free water level. And then, so I've talked about the methods, the fresh state. I've talked about how to measure these, define a pressure curve in the reservoir, in the lab. And then we come on to how we use that data. And this is often called a saturation height function. A lot of people don't like using the term height. It's controversial. In fact, lots of things are controversial about saturation height functions, but I like to just keep it simple. Effectively, we're just finding a way to transform the capillary pressure curves, or these curves that are defined, into a useful model that we can apply in a reservoir. And somebody that taught me about core analysis many years ago described the saturation height function as a stack of capillary pressure curves. But at that time, I didn't know what a capillary pressure curve was, so it wasn't very helpful, but I think he meant well. I've always remembered it. One thing you have to do is make sure that the capillary pressure data is acquired from a representative set of core samples. Otherwise, you're not representing what you actually got in the reservoir. And an example is shown here of what's called a Leverett J function that's commonly applied. In a Leverett J function, the saturation from the capillary pressure curve is linked to both permeability and porosity. and then we take into account we convert the laboratory pressure units into reservoir pressure units, and we're able to come up with a formula where we can apply in the reservoir if we know porosity and permeability, and we know height above free water level, we can calculate water saturation. There are many saturation height functions to choose from. We've got an example here, a case study, if you like. A client came to us and said, this is really strange. We've got a reservoir, and in fact, this reservoir is decommissioned now, so I'm able to share the data. You can see here, rock quality is very high. We've got hundreds, if not thousands of millidarcies. But from the logs, they had a very lazy, very slow change in water saturation with height, and they thought this is not possible. It's a really high reservoir quality. What's going on? So we got them to measure some mercury injection. They didn't want to spend a lot of money, so mercury injection's cheap. We did that, and we created a saturation height model, and that is shown in two ways here. There's a generic curve. The rock quality is reasonably uniform, so the black curve is a generic curve I created, and that exactly shows that we get this lazy change in water saturation over the height of the reservoir. This is the top of the reservoir here. It's a fairly thin column. And then they were able to review and revisit the log-based water saturation interpretations and able to match what we got from core. The red dots, which were deemed stark from a very old core analysis study, they were deemed not to be appropriate because there's been water-based drilling fluid and it hadn't been correctly accounted for. But we can see here that the data we got from the lab helped us to understand this problem, explain and fix this problem for the client. And this is just an example of some of the core here, and we see that the core from this section, they actually cored through, what we say close to the oil water contact, not the free water level. We can see the brown staining, and then the staining becomes less until we come into a more water saturated zone. These are just a couple of quick illustrations of how actually rock quality in the column can absolutely affect what we see. What we can see is rock quality changes with height. We have a lower layer above the gas water contact where water saturation decreases rapidly and then suddenly it increases again. Is this the top of the reservoir? No, absolutely not. The pore throat size has dropped because the rock quality has changed, and therefore it's become the entry pressure of the pore system is now greater than the buoyancy pressure. So it briefly goes back to 100% water saturation before it starts decreasing again. And then we've seen something similar here where we've illustrated again that how the rock quality affects that. So it can look like a stacked contact or stacked reservoirs. It's not the case. It's just down to the entry pressure, the pore radius, and rock quality. And one of the things, again, this can affect barriers in the reservoir. I mentioned that small pores, high entry pressure, well, you can get that same thing in a fault zone where the fault has created very small rock grains. The rock grains have been crushed, the very small pores. They stay water saturated, and so the relative permeability to water is very low. The water saturation, the fault zone is high. It's very difficult for hydrocarbon to cross that, and effectively it's created a baffle or a barrier in the reservoir, and not down to shale or the fault itself, but down to the fact that the grain size has been reduced and the entry pressure has increased. And this is just another example of the same thing where we look at the matrix rock in a reservoir, which shows that low entry pressure, and then we look at the fault rock, which has got a very high entry pressure, and it creates this, what has been termed a wall of water, which could be a complete barrier along a fault, or it could just be a baffle at some point, and the column height will be high enough to allow hydrocarbon to desaturate the pores and move from one side to the other. And this is a nice diagram to study when you get time. I'm not going to go through it all, but I mentioned, things like the transition zone can be a complex thing to define and means different things to different people. And you can see here, there's a lot of annotation on this diagram, and that's, I think I obviously put the credits there. Somebody put this together, and a lot of it, what is the transition zone, what is the irreducible zone? It's down to economics, it's down to the fluid type, it's down to reservoir location, and so I think this diagram illustrates that very nicely. And then over on the right-hand side, we've got some illustrations of what the pores and grain, or what the pores might look like, and the fluid distribution, these different zones where it's fully water saturated below the contact, and then we have hydrocarbon coming in and so on, and then more hydrocarbon and so on as we go up the column. So I think this is a very nice diagram. Take some time to study it, and it's all very relevant to what I've been talking about. So we're coming to the end now, probably taking a few more minutes than I should have, but we can see that the rock properties are very profoundly important. Some of the definitions in the industry have been around a long time, but it'll be quite confusing, but the concepts are very simple. You just need to look at the curve and understand what the different parts are and how they can impact what you're doing if you're trying to model things in a reservoir. And of course, the saturation height function is very important. This whole process involves a lot of careful core measurements, which can take time, but absolutely the information you can get out of them is absolutely vital for reservoir fluid modeling. A lot of reservoirs are not textbook. There's complex situations, and things can affect, other things can affect the fluid distribution. And we can see that not to forget the seal. We come to the top of the reservoir, we haven't exceeded the pore entry pressure, so we have the seal there. And that's all I have. Thank you for your attention.
Thank you very much, Craig. That was quite interesting. Thank you very much. Okay, I think we have few questions coming in. Okay, so first question is, what is your view of computing water saturation on the preserved core sample using techniques such as NMR, T1, T2 scanning, and also NMR isotope analysis like carbon and oxygen isotopes, which links directly to saturation?
Is it possible for me to see these questions in my screen anyway here?
This question is in the Q&A panel, so you can read it there. Yes.
Yeah, I'm trying to find that one. So sorry, maybe I'll ask you to repeat that one. I can't.
Yeah, absolutely. So, what is your view of computing water saturation on the preserved core sample using techniques such as NMR T1, T2 scanning and NMR isotope analysis, like carbon and oxygen isotopes, which links directly to saturation?
Okay. Well, I'm not too familiar with, to be honest with you, I've come across a lot of methods, but those aren't necessarily methods that I would have come across. I don't know, Jules, are you there? Do you have any thoughts on that one?
Yes. So NMR, we know looks at hydrogen. Usually is used to look at hydrogen atoms, which, if you've got oil present in a gas well, it would make it very easy to do. If we replace the gas with the nitrogen, we can then you'll get to quite an accurate view of what water is present. In an oil reservoir, then you need to go through a process of determining first, if you as received, look at the NMR trace from as received, but then cleaning the sample, saturating with 100% water, and looking at the trace with water and comparing the two, we can get a good idea. So, but there are other things you can do there as well. So rather than using hydrogen, you can set your NMR spectrometer to look for sodium, and that's only going to find water. So it's looking specifically at the water in place. So yes, NMR can be a useful tool.
Yeah, I've come across, I think, a lab in the States were using MRI on cores from tar sands to look at water saturation, but I think it's a little bit problematic to get a good answer. I think, I think a dim start always beats everything else, basically.
And then in terms of the carbon and oxygen isotopes, then it's setting up your the NMR tool to specifically consider that region of the spectrometer.
Thanks, Jules. I think you're obviously the man to go to for further insights on that subject.
Okay.
I know
Thank you,
enough
Jules,
to be
and Craig.
dangerous, but yeah, there are other specialists I would go to, but yeah, we do quite a lot of NMR.
Okay, right. So there's quite a few questions now have come in now. So is your example from the Darcy Range Reservoir? In your example from the Darcy Range Reservoir, what was the reason for the low SW values from the install?
I don't know which way slide. Are we talking our particular slide or? Yeah, I mean, I think that all the examples I've shown are, they're all generic. Some of the examples, such capillary pressure curves, I tend to pick a high rock quality and a low rock quality just to show the difference. What you tend to see, if you have a really high rock quality, sometimes the lowest water saturation can be 5, even less than 5%, but that's kind of pushing the limit. It all depends on obviously your column height in the reservoir, what your actual column height is, and what that fluid system is, and what rock quality is. And that's the key thing. If you have an optimal conditions for maximum buoyancy, maximum rock quality, and a good column height, then you will start getting water saturations that are really low. I haven't really seen much less than 5%.
Okay, thank you. So another question, Craig, we have observed that Dean-Stark measurements tend to show higher water saturation than porous plate capillary pressure, even though tracer tests ruled out core invasion during drilling with oil-based mud. Have you seen similar discrepancies, or do you have any insights into possible causes?
No, it's a sort of question that I love, but you need to be able to have access to all the data. There's always an answer, and I love this kind of forensic investigation. There's an answer, and whether it's the porous plate that's wrong, or whether it's the Dean-Stark that's wrong, I don't know. But I say there's always an answer, and it involves going through all the raw data from the Dean-Stark, for example, and the porous plate. I think I did show an example where on an EOR project, and it was a bit interesting because initially the Dean-Stark showed that the water saturation was higher than it was expected, but I had to go back and do a lot of work and go through all the different weighing stages, and I discovered that I used an original dry weight. It actually meant that the water saturation came to a much more believable value, and it's so probably the probable truth is that both will be right in their own way, but it does require a detailed examination of the data in order to say which is right and which is wrong. And obviously that's something I do all the time. That's my job, is to figure these things out on behalf of people. So I can't give you the answer, but yeah, there will be an answer, absolutely.
Okay, all right, thank you. So we've got actually quite a few questions. So we'll take another one. So fun question, Greg. So what's your most annoying, frequently observed crimes against saturation, core analysis or modeling?
The most annoying?
Most annoying or frequently observed crimes against saturation in core analysis or modeling.
Oh, right. Okay. Well, that's a difficult one, actually. I mean, I think people have misconceptions, and I think mercury injection used to have a really bad name. People used to say, well, it can't tell you anything about the reservoir because there is no irreducible saturation. There's test conditions are quite different and so on. But it's all down to how you deal with the data. And when you build a saturation height model, for example, quality control of the data before you start doing it is absolutely critical, because without that, you are doomed to fail. And I've seen a lot of saturation height functions which are over complex. And the reason for their over complex is because whoever's creating them hasn't understood that actually not all the data that you're trying to use is fit for purpose, and you need to do this quality control first. And once you've done that, things tend to all fall in place and things are a lot simpler. And so I think, you know, mercury injection is great, actually. It works nearly every time for me. I think that you do need to ground truth it with some porous plate and some centrifuge, but I think it's had a bad name and it's been abused in the past. And I would say I would like to put that right. Yeah, I don't think I've answered the question, but anyway, that's all I could think of.
Okay, thank you. That actually answered the next question, which is, what is your opinion if using the MICP for estimating modeling irreducible SW? So yeah, you can answer
yes,
that.
So again, we come to the irreducible, and there's no irreducible, but what you would normally do is look at what your column height is in your reservoir, and you would convert that to, obviously, you know, mercury pressure to the in situ column height. Say it was 100 meters, then whatever that was in mercury, you would set that as the maximum water or equivalent water saturation that you would take out of that mercury data set. You wouldn't use something that was a value at 500 meters because you'll never see that in your reservoir. So you would set that cutoff to be representative of your reservoir.
Okay. Okay. So another question is, what is closure correction and how to handle it in lab measurements?
Which correction?
Closure correction.
Okay. Now I think you're talking about on the mercury injection test. What happens is that I didn't have a slide to illustrate it because, as I say, each one of these methods you could talk about it for hours. But when you commence a mercury injection test, because of the mercury's very high surface tension, it takes a while before it conforms, what they call conforms to the surface of the rock sample. And then at some point it enters the pore system. And so what you see from the mercury injection test, it records data, the sort of cumulative injection versus pressure. You will usually see, not always, you'll usually see an inflection where the mercury starts to enter the pore system, and that's your conformance point. And you must subtract that volume of injection from the total volume to calculate the correct saturations. Sometimes that point could be hundreds of psi or even thousands if it's a cap rock. if it's a very permeable rock with large pores, it can be lower than the lowest pressure of the mercury injection test. So in that case, you might miss a little bit of the injection, but that's not so common. Can happen in vuggy carbonates, for example. So I think that's what the question was about. Yeah.
Okay. Right, thank you. So I think we're at the time, but there's a few more questions. I'll try and take some, and not minding that maybe we don't want to take a lot more time over our time. But so what is the preferable method for saturation height function? MICP,
Okay.
centrifuge, or porous plate?
So I was always taught that you should have all of them. Of course, that's nice to have, and sometimes for whatever reason it's not practical. Sometimes people don't want to spend a lot of money. Sometimes they already have mercury injection data available. And I've pointed out the time factor, that it takes a lot of time to get the porous plate, for example, but the porous plate is obviously, it's often captured in conjunction with things like electrical properties. So what you may have a situation where you have a reservoir and you have mercury injection initially because it's available quickly, low cost, and then you create a first pass draft in saturation height model. And then as the core analysis progresses, you will perhaps have some centrifuge and some porous plate data, and then you revisit the model, and hopefully you find that they, you know, have everything's been done correctly, and they quite often do agree with each other. If they don't agree with each other, that's telling you something in it, and you need to look into that. But quite often they do agree with each other. So I would say it would be nice to have all three of them. I would certainly like to have porous plate and mercury injection, but actually, if you really don't have a lot of money to spend, or you need it really quickly, mercury injection is good, excellent, as long as you quality control that data first and understand what you're doing. If you just get a bunch of data and put it into, you know, a software platform that creates a saturation height model, that's not good enough. You need to be careful.
Okay. All right. I'll take one more question. So will core water saturation change in core flood testing?
Absolutely. That's a different thing altogether. I guess you're talking about, because something like you know, a water flood on studies say water saturation will change, but that's not what we're talking about here. Drainage process, which is more of a static process. So yes, it will change. Yeah. I'm quite happy to, if there are any questions which you don't have time for, I'm quite happy to, if you send them to me or we can capture them, I'm quite happy to
we will do that. So yes, thank you very much, Craig. Appreciate the insights and the answers to the questions. Thank you all. This is we have a few more questions unanswered, but we've run out of time. So what we will do is that we will capture them all, and then we will have them. We will reply them, and then we'll email you a response to your questions. Okay. So, Craig, can you move on to the next slide, please?
Yes, I can indeed. Yes.
Okay. Well, thank you very much. I hope you've enjoyed this session. As I mentioned earlier, it's going to be a recording. You'll be receiving a link to the recording of the session. You can follow us on our LinkedIn page for further updates on our webinars, and also our YouTube channel for the recordings of these this session and all the previous ones. Okay. Stay tuned for our next session. We're going to have a little summer recess, so no session for July, but we will be back after that. So yeah, please tune to our updates through our LinkedIn page, and we will keep you posted. Again, thank you all for joining with us, and see you after the summer recess.
Thank you, everyone.
Thank you.